Hello everyone, my name is Adil Wasi. I am a PhD student. I am from Physics Department of Chonam National University, South Korea. The title of my talk is GaN p-GaN core shell nanowire based self-powered piezoelectric pressure sensor. In our group we are growing gallium nitride thin film and gallium nitride nanowires using MOCVD. And we are utilizing these nanostructures in different applications such as piezoelectricity, water splitting, and LED. But in this presentation, I will focus on piezoelectric nanogenerators and piezoelectric pressure sensors. So I will show a few applications of piezoelectric pressure sensors and how we fabricated nanogenerators using pristine nanowires and how we enhanced its performance, and we fabricated the piezoelectric pressure sensor. You know that generally a pressure sensor is a device which detects a force exerted on its surface and converts it to an electronic signal. There are several kinds of pressure sensors. Few of them are based on piezoresistive or piezocapacitive effect, but their drawback is that they lack the self-powered generation property, which is very important property. The pressure sensors which are self-powered, they are either based on triboelectric or piezoelectric effect. The triboelectric pressure sensors, they are easy to fabricate. They exhibit high power density, but their performance is dependent on environmental factors such as humidity. In case of piezoelectric pressure sensors, there are several piezoelectric materials, and the famous one is PZT, lead zirconate titanate. It has high piezoelectric coefficient, but its drawback is that it is toxic. It is not biocompatible. So regarding the third generation semiconductors such as ZNO or gallium nitride, they have Wurtzite crystal structure, they have non-centrosymmetric crystal structure, and because of that property they exhibit the piezoelectric effect. They are biocompatible and they are rarely affected by environment. They exhibit high sensitivity, high power density, and their response is also very fast. So I will talk about it. So these are some of the basic possible applications of self-powered piezoelectric pressure sensors. We can use them in the artificial skin as artificial skin, or we can implant them inside the human body. And the major challenges that as I discussed, the first major challenge is the self-powered generation property. The pressure sensor based on piezoelectric effect, they are self-powered. And the other challenge is that the piezoelectric pressure sensors, they must be biocompatible, they must be flexible if we want to use them as an electronic skin. And the pressure sensors or the piezoelectric pressure sensors, they usually measure the dynamic pressure, and because of the leakage current they are not suitable for the static or quasi-static pressure measurements. But here, how if we enhance the structure, we can achieve this property as well. So I will discuss it. This is the basic concept. Like ideally, there is a Schottky barrier junction. When Schottky barrier junction is created, there is a Schottky barrier height which prevents the flow of electrons, and ideally there should not be screening. These free electron in semiconductor, there are free electrons. So those free electrons screen the piezoelectric potential on real ground. The interfaces have defects and there is a leakage current, and because of that leakage current the piezoelectric potential can be screened by the free carriers. So we have in our group, we have investigated the Schottky junction, we have investigated the homojunction, we have investigated the PN junction, and our conclusion is that the pn-homojunction, the well-grown pn-homojunction and well optimized the resistivity of p-GaN shell, we can suppress the internal screening. So I will discuss about it in my coming slides. So GaN nanowire based flexible pressure sensors. Initially we fabricated the piezoelectric nanogenerator using the pristine GaN nanowires, and then we fabricated the homojunction GaN p-GaN core shell nanowires, and we fabricated the piezoelectric pressure sensor. So these are the results from the piezoelectric nano generator, which is based on the pristine GaN nanowires. And this is the structure. Like, this is the structure. First we grew the gallium nitride nanowires on gallium nitride thin film using the VLS technique, and then we transferred those nanowires on the flexible silicon rubber, ITO deposited silicon rubber, and then we made the top contact. So this SEM image is for the pristine nanowires, and this is for the PDMs encapsulated nanowires. The maximum current that we achieved at different frequency, at high frequency about 10 Hz, we achieved around 900 nanoamperes, 800 900 nanoamperes, and the voltage, maximum voltage was around 14 volt. But the problem was that the voltage response was not stable because of the significant leakage current. And then we moved to the other. So this is the schematic flow for the growth of GaN, p-GaN coaxial nanowires. We used AU deposited gallium nitride thin film. The AU thickness was around 6 angstrom, and then we placed AU deposited gallium nitride inside the MOCVD reactor, and we incorporated the trimethyl indium and trimethyl gallium at different temperatures, and then we did the agglomeration at 825 degrees centigrade. Here you can see the agglomeration. So this is the gallium indium AU alloy agglomeration. So after the agglomeration step, the growth of the nanowires was started, and by introducing the growth species like ammonia and trimethyl gallium around for 500 seconds at 50 torr. So after the growth of pristine nanowires in the same experiment, we started the growth of p-GaN shell. Here you can see. So this is the p-GaN shell. So these are the SEM images. Like the first two SEM images, these are for the agglomeration, agglomerated particles, gallium indium AU alloy agglomerated particles. You can see they are well separated and they are in spherical shape. The middle images, these are the SEM images of pristine nanowires. And their average diameter was around 40 nanometer. And then the bottom two images, these images are for the GaN p-GaN coaxial nanowires. You can see their thickness is enhanced. It is around 300 nanometer. The diameter is around 300 nanometer. And these are the TEM images. The TEM characterization was performed to confirm the crystallographic orientation of the GaN and pristine GaN and GaN p-GaN coaxial nanowires. You can see the lattice despacing. Despacing is around 0.26 nanometer, which is attributed to the C-axis orientation. And similarly, from the diffraction pattern of the pristine and of the diffraction pattern of the GaN p-GaN coaxial nanowires, we can see the nanowires are grown along C-axis. Their crystallographic orientation is C-axis, which was confirmed from despacing and from the diffraction pattern. And the last image, the last figure, it shows the wood side crystal structure, which is oriented along the C-axis. It was originated from the software. And this is the energy dispersive spectroscopy analysis, EDS mapping. We did it to check to confirm the incorporation of magnesium, because the magnesium incorporation it is a difficult job using MOCVD. But in this image you can see, like this is the image for magnesium, and here you can see it is magnesium is incorporated. And this is the device structure. After growing the gallium nitride nanowires on gallium nitride thin film, we transferred the nanowires. Like first we have grown the gallium nitride nanowires on gallium nitride thin film. Then we encapsulated the nanowires inside PDMS using spin coating technique, and then we transferred the nanowire PDMS matrix, PDMS encapsulated nanowires using doctor plating technique. In this image you can see, and after that we transferred this nanowire PDMS matrix on the tungsten substrate, and then we deposited the top contact NiASU. So this is the stable voltage response when we applied a pressure of 2 kilopascal. And here you can see the 3 lines like piezoelectric pressure sensor 1, piezoelectric pressure sensor 2, and piezoelectric pressure sensor 3, like PEPS1, PEPS2, and PEPS3. So PEPS1, it has high resistivity because of the more Ng incorporation. So in the longer decay time constant is 19,000. It is because of the high resistivity of p-GaN shell. And the piezoelectric pressure sensor with low resistivity, it exhibited the low decay time constant. And in case of pristine nanowires, the decay time constant is only 4 seconds, which shows that the significant leakage current. And because of the stable response of piezoelectric pressure sensor 1, we tested it for its sensing ability, and you can see this graph. And this is the linearity. Linearity factor is around 0.992. And here we, to confirm its self-power generation property, we measured its power density by connecting the load resistance, and the maximum power density is around 70 microwatt at 6 mega ohm. And then we also charged a capacitor, and the filling factor we observed it is 0.26. The durability, its durability, long-term durability was tested for consecutive 3 days, and we observed only 3% degradation in the output voltage with a continuous measurement for 3 days at 1 Hz frequency. So this was about the GaN p-GaN coaxial nanowire based pressure sensor, in which we suppressed the leakage current, and because of that reason the voltage decay time constant was enhanced. And the summary is that the GaN p-GaN coaxial nanowire based piezoelectric pressure sensor, it exhibited high power density, and the fill factor was around 0.26. It exhibited enhanced sensitivity 14.25 volt per kilopascal and linearity of 0.992. And the main thing is that we observed the longer decay time constant, which is because of this decay time constant we can measure the static pressures, because the voltage response is stable for 500 seconds. It is purely stable, so it is in this region we can measure the static pressure. Then the enhanced performance of pressure sensors is attributed to the high quality rectifying pn-homojunction and high resistivity of p-GaN. Yeah, because this is online, so in case if you have questions, I will attend the Zoom meeting, so you can prepare your question and you can ask in the Zoom meeting. Thank you.